Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 14. Today, we're going to talk about a phenomenon known as the Central Limit Theorem. That's really a miraculous result, which comes from this apparent convergence of probability distributions whenever you do something enough times. Let me show you some examples. This comes from Pittman's probability textbook, which we've sort of been using unofficially for our course. This is, in the first row, a few examples of the Bernoulli distribution. So remember, with the Bernoulli random variable, you have two outcomes, 0 and 1, 0 with probability Q and 1 with probability P. So when you look at P being an eighth, that means the success is much less likely. And so most of your attempts tend to be failures. And of course, as you change P and you let it go to a half, now you have an equal 50-50 chance of success or failure. And then of course, on the flip side, if suddenly your probability of success is much higher, things tend to land in that bucket. Now this is what happens when you just look at a single instance of your sort of biased coin flip. Here, the probability of a heads 1 is only an eighth, so tails is much more likely. And over here, let's say the probability of heads is more likely it's 3/4. Now what happens when you repeat this experiment with fixed probability of success P? So that's what's going to be fixed as we move down in these columns. A surprising pattern emerges, and what I'm showing you here is, again, the binomial distribution. So I'm counting the number of successes out of n tries. So for n equals 1, that's the same thing as just doing it once. But as I go higher and higher, you'll see that this shape emerges. This is the shape which looks a lot like this normal distribution that we introduced last time. Somewhat surprisingly, even if you have a small chance of success and you just let n grow. So here you'll have this shape here. You'll see this sort of traveling wave pattern where things will become a little more spread out, and consequently that peak will go down. But if I were to sort of bend and sort of squeeze in my axis here for the number of heads, you can imagine how it would still kind of look like the same universal shape, just sort of displaced by some multiple of n. Just to sort of prove my point earlier, so here we have a situation where n equals 100. So this is a situation where even if I have a coin which is highly biased not to come up heads, so meaning tails comes up 90% of the time, heads comes up only 10% of the time, and I flip it 100 times. Of course, two slides back here, when I just looked at 8, it didn't look much like this curve here in the middle. But notice when I do it 100 times, actually this curve does seem to concentrate in this sort of bell-shaped curve, which is the normal distribution, or the Gaussian. And again, this is stable across parameter values for success. So when you have a 20% chance of heads, you still get this pattern, 30, 40, all the way up back over here. Notice again, you get these bell-shaped patterns again and again and again and again. Now, in all these cases, I'm looking at the binomial distribution for large n for varying p. Let me show you what happens if we consider a situation where we look at a different distribution, but still when I sum that distribution enough times, I'm curious what sort of pattern emerges. So if the thing I'm looking for, yes, looks like this. So as before, we have, and again, this is from Pittman's probability. If I look at the roll of a die, a fair six-sided die, then I know that each of these outcomes is equally likely. So each of these has a height of 1/6. It's just a visual way of thinking about our probability mass function, our probability table. Now let's imagine I roll that die twice and I sum the outcomes of the rolls. Notice that we get this sort of shape that peaks in the middle, which sort of corresponds to the fact that things tend to kind of average out. And again, as I increase the number of times I roll my die, and I look at the distribution of possible sums when I roll my die, I guess I have n equals 2, 4, 8, 16, all the way up to 32. Somewhat remarkably, the same sort of curve appears. And notice that rolling a die is very different than flipping a coin, because for a die, there are 6 possible outcomes. But nevertheless, when I roll my die enough times and I sum the outcomes, I end up getting a shape that looked a lot like that sort of large N version of the binomial distribution. Even if you have sort of a staggered distribution, so here's something where I have 3 outcomes, and 1 is less likely than 2, which is less likely than 3. If I repeat this summing experiment, I look at Sn, where this is xi, and here I'm looking, let's say, at this is 4, so here's S4 equals x1 plus x2 plus x3 plus x4, where this is my xi. So these are independent and identically distributed. When I let n get large enough, again, the same pattern emerges. And I can take really wonky distributions, things that are sort of concentrated at uneven intervals. And again, maybe you get some weird sort of reinforcement patterns when you sum the possible outcomes. But again, for large enough n, and this is n, equal to 32, then the same pattern emerges. So today's lecture is going to be exploring where this pattern comes from and applying this pattern. Again, this isn't necessarily a proof-based course, but once we've identified the pattern, we want to exploit it and leverage as many observations as we can. So let's get back to it. So this is lecture 14, and we're going to explore the central limit theorem. So first, I want you to recall that last time we discussed this notion of the normal distribution. And so we said that the probability density function also called PDF for a normal distribution, a normally distributed random variable, X. And we're going to need to specify 2 parameters in order to write down an equation for this probability density function. And so here we're going to assume that the expectation of X is mu, and the standard deviation of X is equal to sigma. Then the probability density function, which we sometimes write as f big X little x, is equal to 1 over sigma times the square root of 2 pi e to the minus x minus mu squared over 2 sigma squared. To make dependence on the parameters mu and sigma really explicit, sometimes we call this phi mu sigma of X. And this phi comes from the fact that this normal distribution, as we just saw, appears everywhere. And so it's so special, we're not going to just call it generic old f, we're actually going to call it phi. Remember what a PDF means is that if I want to know the probability that X lies between 2 values, A and B, then what I have to do is integrate this function, biv at x dx, between those values A and B. And so to sort of draw a picture, imagine I've got my bell curve here. It's centered and symmetric around mu, and has some standard deviation sigma. But if I want to know what the probability that X lands between, let's say, A and B, then what I can do is compute that probability by integrating this function with those limits. So essentially I'm finding the area under the curve here, and this is going to be my probability that x lands between A and B. So again, you should think of these probability density functions as just a continuous analog of the histograms I was just showing you. And so if I want to compute the probability of it being a certain interval in my histogram, I just sum up the heights of my histogram, and then you can imagine how in the limit that sort of corresponds to, all right, maybe I shrink the size of my rectangles and then I go lighter. Essentially, you get this like Riemann approximation of the integral. Now, as I tried to emphasize last time, so this function here, so I'm going to ask you to note well, nota bene, phi mu sigma of x has no nice antiderivative. Meaning that when it goes to actually compute this integral, you don't do it the way you normally did in calculus, which is, you have to take this function, compute its antiderivative, and then evaluate that antiderivative at its two endpoints. The reason why this doesn't have a nice antiderivative is actually a very deep problem. But nevertheless, this pattern, as you can see, is so universal that we've had to figure out numerical means for computing it. And moreover, since we're going to compute it, we don't want to have to keep computing it. So we just want to compute it once and for all, and we're going to just leave it at that. But this also means we need to standardize our normally distributed random variable so that it fits, let's say, a convention, which says that I'm going to only compute these integrals for when mu is equal to 0 and sigma is equal to 1. I mean, think about it. If we didn't do that, that means that we'd have to have a copy of this sort of z table, which I introduced last time, that has a separate sheet for every possible value of mu and sigma. I mean, that's just absurd. All right, so what we do instead is transform we must transform our random variable x to capital Z, which is going to be defined as x minus mu divided by sigma. And what this then means is that we can compute the probability of x lying between 2 points A and B by instead computing the probability that Z lies between what I'll call A star and B star, where A star is just the result of applying this formula, x minus mu over sigma. In other words, it's just the Z value associated to A. So this is A minus mu divided by sigma. All we're doing is we're just converting our A and B into number of standard deviations from the mean. So these are just the Z values for this. And one of the reasons why this is nicer is that once we do this, we can compute this in terms of the integral of a somewhat simpler looking function, one that looks just like this. So 1 over square root of 2 pi e to the minus z squared over 2 dz. And so what we end up calling this first of all, this guy right here, we end up calling this just little phi. And we don't write down mu sub sigma, mu or sigma, because we know that mu is equal to 0 and sigma is equal to 1. And then we call its antiderivative capital phi. So this is then going to be b star minus phi of a star. And this becomes now the way in which we compute the probability of a normally distributed random variable landing between values a and b is we first standardize, meaning we compute this a star and b star, and then we plug into our z table the way for basically looking up this lower tail probability. So this is essentially the lower tail probability at b, and this is the lower tail probability at a. So that's what phi stands for. And then this is going to be, just to try to match the picture a bit, that's going to be our b star. And so again, by taking the difference between these two areas, you compute this area right here. All right, so again, that's just a little bit of a warm up for remembering how we compute probabilities using this normal distribution. Now, the reason why I'm bringing this up is because we just saw that when we sum together enough random variables, we actually get something that looks a lot like a normal distribution. So being able to compute things using this, this formula is going to be very important. All right, so let me go ahead and warm up with the first thing we just introduced. Or maybe I'll note some special cases, actually. So let me just do that real quick. So again, we say, so let me just write a quick remark. We say x tilde norm mu sigma to mean it has a PDF that looks like phi mu sigma, and that's the way in which we can compute probabilities. And in particular, then when z looks like this, let me see, it's normally distributed. And then sometimes when we look at mu equals 0, sigma equals 1, we mean that this is the, so z, which looks like that, is unit normal. All right. Now, there's another thing to note, which is that in the situation where we're looking at a symmetric interval, so when we want to compute let's say probability that x is concentrated between a certain interval, let's say minus cx sorry, let me just write it this way. So when we want to compute probability that z is between minus little z and positive little z, for z that's unit normal, then if you plug it into the equation that we just wrote, this looks like phi of z minus phi of minus little z. But if you kind of think about it, and again, this is 0, and let's say this is minus z, this should be the same thing as 1 minus phi of z, because remember, by the rule of complements, if this is ordinary z, then this should be 1 minus phi of z, because again, phi of z is going to be, for positive, something that goes up and above 0. And so then when I look at the upper tail probability, that's the same thing as computing this, 1 minus phi of z. So if I use that, I then get that this is the same thing as, 1 minus phi of z, which is then the same thing as 2 times phi of z minus 1. So that's going to be, and this actually comes up so often that we sometimes give this a special name, minus phi of z to capital Z. And that just indicates that if you want to know the probability that a unit normal lies between plus or minus a fixed value, little z, you can just compute 2 times phi of z in your table over here, and then just take minus 1 from that. All right. So if you remember, when I first started and I looked at going back a bit, this distribution of values for this distribution of values for the binomial random variable, I got this shape. And so often we sometimes just call this the normal approximation to a binomial. Or I like to sometimes call it the baby central limit theorem. And we can write this as binomial bin in P. And it says essentially this. It says that, so remember that if x1, x2 on up through xn are IID Bernoulli's, also called indicator random variables, then we know a couple things. So we know that each of these xi have mean p, and we also know that the standard deviation of each of these xi's is equal to the square root of p times q. So in the situation where we consider Sn, which is the sum of these in Bernoulli's or in indicators, we write that this Sn is binomially distributed with parameter p and number of tries n. And so what the baby central limit theorem says is that if I want to know the probability that Sn lands in a certain range, then what I can do is instead compute this area under the curve of the normal distribution at 2 specific values, specifically b minus np and then dividing this by NPQ. And the reason for this is, recall that the expectation of Sn is equal to n times p, and the standard deviation of Sn is the square root of NPQ. And then once I do that, I can then also compute the associated standardization or z value for A. By square root of NPQ. And so this is a extremely handy formula. And I'll note that there's also sometimes used a something called a continuity correction, because with the binomial random variable, you're counting the number of successes, and those are always integers. And so we might want to include the endpoint when this, say, NP is not an integer, even though this is going to be an integer. And so sometimes you'll also see a better approximation, which uses the continuity correction with the continuity you'll see that this is equal to phi of b plus a half minus np divided by square root of npq minus phi of a minus a half minus np divided by square root of npq. All right, so let's go ahead and see how this works in action. So, and sometimes I'll include the continuity correction, but more often than not, it doesn't really matter. I will say a quick remark, which is we can say that this is a good approximation as long as n times p times q is greater than 10. Although sometimes we'll go a little bit lower, and we'll see that it's still a pretty good approximation. All right, so let's do problems. And again, in class, when we meet and work through some exercises, you're gonna really be focusing on drilling this kind of method. So let's go ahead and get down to it. So here's an example application. So imagine we've got two people. I think I call them Jane and Alex. And they're about to take a 48 question true false test. Question. So Jane is going to be the sort of good student who usually gets questions right 75% of the time. Alex, on the other hand, is just guessing. So that means because it's a true false test, he's going to be right 50% of the time. But of course, both Jane and Alex want to pass. And let's say that passing equals 30 or more correct answers. So let's first compute the probability of Jane passing. So that means that if we define J to be the score that Jane receives on an exam, then we're asking that we want j to be greater than or equal to 30. But again, we should think of this as a binomial with probability of, what did I call it over here? So yeah, NP, so this is binomial with 48 and P equaling 3/4. Of course, you can never score higher than 48. So we have this bound. Oops. So we can think of this as sort of an SN with this N being 48 and P equaling 3/4. So what's the probability that Jane scores in this range? Well, you could compute it directly using this sort of complicated expression where you do, the exact way would look something like this. So we're gonna have to sum from k equals 30 to 48 of 48, choose k, 3/4 to the k, 1/4 to the 48 minus k. But you can see we've already got like 18, 19 terms in there. And that's not a sum any of us want to do. And moreover, these, especially with 48, it's going to be a pretty large number of options here. So if we instead apply the baby central limit theorem, we can instead say that this is approximately equal to phi of, so first I have to do b here, right? So that's 48 minus n times p divided by the square root of npq. And this is then going to subtracted from phi of 30 minus n times p over the square root of npq. So what does NP and NPQ work out to be in our case? Well, let's see. So N times P is the same thing as 48 times 3/4, which ends up equaling 36. That's the expected number of questions that Jane's going to get right. She gets 75% on the exam. Well, 75% of 48 is 36. Now, what about the standard deviation? Well, now I have to take square root of NPQ. So I end up taking, well, that's already NP right there. So here's 36 times 1/4. Well, 36 is 9 times 4. So this ends up equaling square root of 9, which is 3. All right, so now I can actually compute these values. So now I'm going to look up phi of 48 minus 36, which is 12 divided by 3, minus phi of, well, 30 minus 36 gives me -6 divided by 3. And so now I just need to look up what is phi of 4 minus phi of -2 in my z table. So now let's go look up in my z table. So just to take a quick trip over here. So first of all, if we're more than 4 standard deviations to the right, you can already see that we're essentially equal to 1. The last entry in the z table is 0.9998. You can see that right there in the lower right-hand corner. So I'm going to treat phi of 4 as 1, and that's a very good approximation. Now, what's phi of -2? Well, to find that, I need to go back here, find -2 in my column here. Luckily, I don't have any other decimals to go out, so I can just read this off. It's 0.0228. So this ends up equaling approximately 1 minus 0.0228. So let's just call it about a 98% chance of passing. All right, 97 and change, 97.702, something like that. All right, so Jane is set. Now, if you want a little exercise, do this with the continuity correction. Well, all that's going to involve is then I'm going to take phi of 12.5 divided by 3, which is already greater than phi of 4, so that's not going to change anything. And then if I do this, I've got minus 6 minus 0.5, so that's going to be minus 6.5 divided by 3. All right, so if I were to plug that in a calculator or something, I would say that that's even more than that's what? Minus 2. I'll just go ahead and do it here. So 6.5 divided by 3 equals 2.1. So it's minus 2.166. So going back over to the z table, 2.16. All right, well, first I find 2.1 right there in the gray row. And then I need to go over to 6, 2.16. So that ends up being 0.0154. So we'd end up getting even better. So 1 minus 0.0154. All right, so that really is about a 98.46% chance of passing. All right, so I'm not going to do the continuity correction again, but I think that should give you the basic idea. So now let's compute probability of Alex passing. Well, first we need to compute n times p for Alex, which is going to be half of 48, which is 24. Remember, he needs to hit 30, so that means he has to definitely do better than just guessing at random. And moreover, if we compute Alex's standard deviation, well, this is going to end up being square root of 24 times a half, because again, this is already in p, so that's square root of 12. And I think square root of 12 ends up working out to be something like 1.7. Well, here, we'll go ahead and I'll save the calculation for a little bit later. Yeah, so this is equal to approximately 3.46. So again, this may seem really complicated, but at the end of the day, all you have to do is just compute the z values for 30 and 48. I think we already see here that the probability of Alex passing, which is A between 30 and 48, well, this ends up equaling phi of 48 minus 24 divided by the square root of 12 minus phi of 48, sorry, 30 minus 24 divided by the square root of 12. Now, again, this is going to basically be, this is basically going to be 1, because there we're looking at almost 5, maybe even 6 standard deviations above the mean, where phi is definitely equal to 1. But now down over here, we're looking at, if I plug in my calculator, what this looks like 1 minus phi of 1.73. Now again, what I have to do is go over to my z table and find where is 1.73 on this. Well, there's, all right, 1.7, again, a gray row. And then I need to go over a couple entries, 4 entries to get 1.73. I read that as 0.9582. So this is 1 minus 0.9582. This means that Alex has less than a 4% chance of passing. And again, this just indicates that even if Alex gets lucky, he needs to get really, really lucky. In fact, more than 2 standard deviations away above the mean lucky, which again, when we looked at the 68, 95, 99.7 rule, it's not something that he can really count on all the time. Well, maybe he can count on it happening 4% of the time, but aren't enough exams for those odds to work out for him. All right, so let's do another coin, and let's try to connect with that some of these back of the envelope calculations that I alluded to. So let's do another example. Suppose I flip a fair coin 100 times. What range of heads accounts for 95% of all observations? Meaning, suppose I wake up every morning, I have a weird ritual. I get up, I flip my coin 100 times, I count the number of heads, I write it down on a piece of paper, and I do this every day. I want to understand what is the range of possibilities that will fit roughly 95% of all days. Well, here's a situation where you can very much like use the 68, 95, 99.7 rule. So remember the 68, 95, 99.7 rule. And of course, I should be a little more precise here and try to pick an interval that's sort of symmetric. So maybe I'll say this, some symmetric range. Is going to account for 95% of observations. Remember, this corresponds to 1 sigma, 2 sigma, or 3 sigma standard deviations. So what I'm looking for here is, again, the baby central limit theorem says that number of heads with 100 flips. Well, I've even got the plot right up here. It's going to look something like this. And so I'm going to try to find an interval that fits 95% of all results, which means I need to go above and below 2 standard deviations. Well, what is 2 standard deviations? So let me go n times p plus or minus 2 sigma. Well, that's 100 times a half plus or minus 2 times the square root of NPQ. All right, and what is NPQ here? Well, that's 100 times a half times a half. So that's a quarter of 100 is 25. This ends up equaling 5. So the answer is that 50 plus or minus 10 heads accounts for 95% of all observations. All right, we're going to do a lot more examples, but they're all essentially going to have the same sort of feel. Let's go ahead and state the sort of grown-up central limit theorem. This is going to be the, well, you know, of course, with age, we all become a little darker. So let me do that. So now we have the grown-up. And what the grown-up central limit theorem essentially says is that it didn't have to be a binomial, meaning we didn't need to look at a sequence of xi where xi was Bernoulli. In fact, any random variable, as long as we are using the same one and we're doing a bunch of tries with it, the sum of these random variables is going to converge on this normal distribution. And then consequently, it's going to converge on the unit normal distribution once we've standardized appropriately by subtracting off the mean and standard deviation. So let's go ahead and write this down. So if x1, x2, on through xn are IID random variables with each of the xi's, again, IID means independent and identically distributed. So in particular, their mean and standard deviation are the same. Then the probability of Sn landing between two values where Sn is the sum of x1 through xn is well approximated by, meaning you really can't tell the difference, by this formula. B A minus n mu sigma times square root. And so again, this is a super important formula. So I'm going to put it in a big block red. And this is going to include the binomial version as a consequence, because remember, mu in that case was p, and sigma was square root of np. So note when Sn is binomial, mu equals p and sigma equals square root of pq. So you get the same thing we just wrote down, but now this works for rolling die and the sort of weird looking distributions we already considered. Of course, you can also use the continuity correction if you want, but let's not worry about that. When each of these xi have possible values that are consecutive integers. But again, that's just sort of a side note. Right now, I just want you to really focus on computing this value. Again, even though it seems kind of complicated, all you have to do is compute these values, look it up in the Z table, and you're done. All right, so let's go ahead and see this in action. And let's consider a distribution or collection of xi's that aren't Bernoulli. And let's go with one that actually kind of almost looks Bernoulli. And this is an application which is sometimes called the Drunkards Walk. But it's also a wonderful model for diffusion. Right, so let's imagine, we've got, our drunkard. All right, doesn't really know what he's doing. And essentially, he either stays in place with a probability of a third, or he steps left with a probability of a third, or he steps right with a probability of a third. And so we're now going to just let time evolve. So maybe he stays for a bit, maybe he stumbles a little bit that way, and maybe he stumbles back. In general, at any time step, we model displacement as this random variable xi, which is -1 with probability a third, 0 with probability a third, and +1 with probability a third. So it's a uniform distribution on -1 to 1. So xi is uniform on -1, 0, 1. All right, that's just a shorthand for that. Here's our question. After 10,000 time steps, what's the probability that this drunkard has managed to actually make any progress? Let's say it has moved 100 steps to the right. So what's the probability that Sn is greater than 100? Well, again, we just need to compute n times mu and sigma times the square root of n. So answer. So apply central limit theorem. This probability is the same thing as 1 minus the probability that he stays closer or goes to the left 100 steps. So 1 minus phi of, well, let's look at the formula again. It looks like 100 minus n times mu divided by sigma times the square root of n. Now, what do we expect here? So note the expectation of xi, which is the definition of mu, is equal to 0. He's equally likely to stumble back and forward to then, or stay where he is. You can check this by just computing that -1 happens with a probability of a third, +0 happens with a probability of a third, but then +1 also happens with probability of a third. And so these guys cancel and you get 0. Now, how do we compute the standard deviation? Well, you can just compute, in this case, v of xi to be e of xi squared, times mu squared, which is 0 squared. And so that just ends up being 1 times the third, or -1 squared, plus 0 squared times the third, plus 1 squared times the third, which ends up equaling 2/3. So that means that the standard deviation of xi ends up being the square root of 2/3. All right, so let's plug it all in. So now I just need to look up in Z table phi of 100 minus 0 divided by square root of 2/3 times the square root of 10,000. 10,000 turns out to be 10 to the 4th, so this ends up equaling 100. This ends up equaling phi of, or at least the argument equals 100 divided by, well, 2/3 of, or square root of 2/3 times 100 ends up being about 81.65. And so if you, again, go to your Z table, maybe let me just go ahead and clear it. So it's 100 divided by 81.65. This is phi of 1.224. Go to my Z table. 1.22 is about 0.88, repeating. So 1 minus 0.88 repeating ends up equaling about 11%. Right, I mean, round that up to 0.89, and then you add, and you get that that's a 0.11, which is 11%. So again, even though this looks complicated, it's not so hard. You just are computing these Z values associated to different choices of N, mu, and sigma. That's all you need to know, N, mu, and sigma. All right, let's do another application. And this is really an important application, which goes to at the heart of what happens whenever we carry out an election. We want to figure out what percentage of people want to vote for one candidate or the other. This is a process of estimation. And often what we do is we have to go out in the world and talk to people, but we can't talk to everyone, so we don't know the true percentages. But we maybe will sample a subset of the population and try to say that that's going to be a decent approximation of how people actually feel. Of course, there are all sorts of problems with that method, but in less fraught subjects other than politics, this is actually a really good principle for a lot of science. So let me talk about confidence intervals. So. Right. So one of the things that the Central Limit Theorem allows us to do, it allows us to give much better bounds on estimating percentages or proportions. I'll call it, that's the average number of people who feel a certain way. Let's call it mu of, which is the expectation of xi. And the way we estimate this is we use empirical means, which I'll call x bar, which is the same thing as Sn divided by n. And so again, the key thing here is you take a bunch of outcomes drawn from some xi's, you add them up together, you compute the average by dividing by n, and we want to say that this somehow approximates the true mean, which is mu. Now, for now, I'm going to actually assume that we know which is the true standard deviation. Turns out we can drop this. And use instead something called the sample standard deviation, which ends up looking a lot like the ordinary variance, but is divided by n minus 1. So, but I'm going to ignore that for now. That's more of a subject for statistics and not probability for statistics. So anyhow, what's the basic idea here? So here's the basic problem. Suppose we want to estimate mu up to some precision epsilon. And let's go ahead and further say that I want to be 95% sure. So let's say if we want to determine mu up to precision epsilon with, let's say, a 95% confidence. Of course, you can use other values, but you'll have to just sub in where you see 95. What you're trying to do is do the following. So you're trying to bound the probability that Sn divided by n minus the true mean mu. We want that this to be within epsilon of the true answer more than 95% of the time. So that's where that. You'll see in general that people will instead sometimes call this 1 minus alpha, where alpha is the confidence level. Here, we're using alpha equals a 0.5, which sometimes also gets that notion of a p-value. But anyhow, for now, right now, we're just going to try to compute this as is. Now, I claim that the central limit theorem allows us to answer this question. So this is equivalent to asking that when I look at n times mu, which is, again, the expectation of Sn, and I subtract n times epsilon, so that's the deviation I'm allowing myself from that mu, I want Sn to then be in this range. I leave it to you to check that these things are equivalent. So now we're in business because you can just literally let this be, let's call that A, and let's call this B. And by using the central limit theorem, this is equivalent to phi of B minus n times mu divided by sigma times the square root of n minus phi of A minus n mu divided by sigma times the square root of n. Where again, maybe I'll be a little more colorful here. And I'll say that this is minus B minus A. Now, of course, if we plug this back in, what we end up getting is that this is phi times, well, n mu is going to cancel, and it's going to leave an n epsilon behind. And then I'm subtracting here. Same thing, minus n mu. So again, the n mu's cancel, but now I have a minus n epsilon up top. So if you go back and you remember, I called this, let me just go ahead and do another simplification here. So n goes into that. This ends up turning into square root of n up top because n is just square root of n squared. So this ends up equaling phi of minus square root of n times epsilon over sigma square root of n times epsilon sigma, which using that whole, take the complement and then subtract and add, this ends up being 2 times phi times the square root of n times epsilon over sigma minus 1. So really what we're saying here then is that I want this expression here to be greater than 0.95. Because again, this expression here does a damn good job of approximating this right here. So finally, so now let me go ahead and plug that in. So I've got, I want 2 times phi of square root of n epsilon over sigma minus 1 to be greater than or equal to 0.95. Again, in general, I would say this is equal to 1 minus alpha, where you choose alpha. But then I can solve, and I'll say that this is the same thing as phi square root of n epsilon over sigma being greater than or equal to 1.95. I add 1 to both sides and I divide by 2, which ends up equaling 0.975. So I need to then find the smallest value. So I'm going to do what's called a reverse z-table lookup. In order to find, oops. So what we're trying to find here is find smallest z such that phi of z is greater than or equal to 0.975. And so that's what we're doing here. Because I want this inequality to be true. I know now the value in the table that I want. So now I need to reverse engineer and find which z gives me that value in the table. So let's do it. Let me go over. I'm looking for 0.975. I've got it right there. It seems to correspond to 1.9 for z, the first few digits, and then 06. So 1.96 is going to be the thing that gets me to 0.975, and anything larger than that will shoot over. So if I do that, and now I get that z has to be greater than 1.96. All right, so almost done now, because there's 2 high-level lessons here. So we now know one of 2 things. So suppose we know how accurate we want to be, trying to determine an election, and it's very, very important that we determine it within, let's say, a single percentage point. Sometimes we need even finer than that, half a percentage point. That's a situation where we know epsilon. And then in that setting, in order to guarantee that phi of square root of n times epsilon over sigma, to make that greater than 0.975, which was the thing we needed in order to be 95% confident, then to ensure we need square root of n times epsilon over sigma to be greater than or equal to the z value, which we found puts us above 0.975, which was 1.96. This was the result from our reverse lookup. So in other words, as long as n is greater than or equal to 1.96 times sigma divided by epsilon squared, then we can be 95% certain. And notice that the smaller and smaller we make epsilon, and epsilon's here in the denominator, means the limit as we go to 0, we're getting closer to dividing by 0, which makes this quantity really large, which is going to push n to be really large. So that makes intuitive sense. The more accurate we want to be, the more number of times we're going to need to sample and ask people. We can also go the other direction, which is, suppose we know n, then we can give a lower bound on the spread or error in our measurements. And that's one of the reasons why we use the letter epsilon. Epsilon looks like E for error. We know that then our error has to be at least greater than, well, just by solving this inequality again, we have to have 1.96 divided by the square root of n times sigma. And this is sometimes called the square root law. Which essentially says that our error is going to be proportional to 1 over the square root of the number of times we try something or measure something. As our final application, and I know this lecture is going a little long, I want to consider something that we did at the very end of lecture 13. So just, if you remember here, we introduced Chebyshev's inequality, which just doesn't require a sum of random variables, just as for an arbitrary random variable. But we used it to then leverage something about the law of averages. So here we looked at x equaling an, which is like our x bar. And if you look at this, you'll see I asked how many times do we need to roll a fair six-sided die to be within 1/2 of the true mean, which is 3.5, 95% of the time. When we did this calculation, we got something like n was greater than or equal to 234. So that means we had to roll 234 times in order to make sure our measurement was going to be within 0.5 of the true mean 95% of the time. Let's see, and that was the bound or the number given to us by Chebyshev. Let's see what the central limit theorem says for us. So if we revisit, let's do this example. So roll a six-sided die. We want to do this. So if we want epsilon to equal 0.5, same thing as a half, then what we're end up solving is n needs to be greater than or equal to 1.96 times sigma divided by epsilon, and then we take that quantity squared. Now, again, if we remember that sigma for a six-sided die is our standard deviation, ends up being 35/12. And so this epsilon ends up being 2 times this. We end up getting that this is actually only about 44.81. So this is a huge improvement versus the Chebyshev bound of n being greater than or equal to 243. So by knowing that the central limit theorem holds, we can actually say that we only need to roll our six-sided dice 45 times in order to make sure that I'm within 1/2 of the true mean. But let's go ahead and apply this flip direction. So if we do, so this is an example of applying the first thing. Suppose we know instead n is equal to 243. Then the lower bound on our error is 1.96 times the square root of 35/12 divided by the square root of 243. You plug that in a calculator, you end up getting that this is approximately 0.218. So now we know that our error, if we actually rolled it that 243 times, wasn't just a half. Actually, we had a much narrower spectrum of possibilities. And so we got that the error band was only 0.21 above and below. So again, if we had our sort of true mean mu, then our 95% confidence interval in this case looks something like 2 times the standard deviation over the square root of n. So this ends up equaling minus 2 times the standard deviation divided by the square root of n. So here I'm just replacing 1.96 with 2. So I'll just go ahead and say that error, so 95% confidence interval is going to be whatever your numerically measured proportion is, plus or minus 2 times sigma divided by the square root of n. And so this is another expression of the square root law. And so that's why when you look at any data and they say, well, this percentage of people are helped by a medicine, they also need to report what their confidence interval is, which is going to tell you roughly how many people were in the study or the sample or how many people they polled. So you can really see here how the central limit theorem has sort of infiltrated every part of our scientific lives, whether it's political science, determining who people are likely to vote for, or if it's doing sort of science related to medicine and testing things like this, we want to look at results there. All right, so that's it for today. Look forward to seeing you soon.